Hello, good morning. How's everyone doing today?
Good morning.
Hi. Okay, so we left with this problem from our previous class. Just want to let you know we cannot completely solve this problem yet, but as we go on, we will expand more into, okay, how do you calculate a normal force on the ramp? How do you calculate different kind of friction? And how do you calculate a spring force? So as we expand into those details, we will be able to solve more and more problems. For example, for this particular question, you're sliding a book across a table at a constant velocity. What we can do, we can solve for the normal force. But in terms of what is the magnitude of the force your hand applies, we do need to wait until we expand more details on the friction to be able to solve it. But first, let's just take a look at how to draw the free body diagram for this situation. You have, in the x direction, you have the force from your hand, and you have the kinetic friction. And then the y direction, you have the gravity of the book, and you also have the normal force acting on the book by the table. So here you have 4 forces, and you label them. You draw your free body diagram like this. Okay. And then we will set up Newton's second law in the both in x and y direction. So let's continue to look at that. For the force in the x direction, right? When you do F net equals ma, when you applied it in the x direction, you add up all the forces in that direction. So if you define a positive direction to be in the direction of where the force from the hand is, then you will write that as positive, right? So the friction would be negative. You have a minus sign. And now equal to the mass times acceleration in the x direction, and that is 0. Now we know the acceleration is 0 because the question said you're moving it with a constant velocity, so therefore the acceleration is 0. You do the same thing for the y direction, adding up the 2 forces. And if you define the upward to be positive, your normal force would be positive, and your gravity is negative, so there is a minus sign. And again, we know that the book is not accelerating in the y direction, right? So that's just implied in the problem, so there's 0 as well. So this is something pretty straightforward in that all the forces are balanced. X and y direction are both balanced. So right away, you know the normal force is simply just balance out gravity, which is equal to the weight of the book. That is 2.5 pounds. So here you don't really have to convert that to kilograms because your final result needs to be a force. And pounds is already a unit for the force, right? So you don't have to convert it. You will just say it is equal to the weight of the book, which is 2.5 pounds. And you know that the force from your hand would be equal to the kinetic friction. At this point, we don't know how to calculate friction yet, but we will talk more about it later in today's class. So now let's move on to looking at more on the normal force. So when we say something is sitting on the table, or even if it's moving with a constant velocity, the normal force is easy, right? It's just going to equal to the weight. Here we're looking at a little bit different situation for the normal force. You have a person standing on the bathroom scale, and that whole thing is put inside an elevator. Now your elevator starts accelerating upward, knowing that all objects within that elevator will be having that same acceleration. So you know that the person you have the same acceleration is upward, even though it didn't say explicitly, right? So you also have the same acceleration that's upward. What will happen to the reading of the bathroom scale? Now here, the hint is whatever you measure, the weight that you measure equal to the amount of normal force acting on you. Okay, so if you think the bathroom scale is providing more of a normal force for you, then your read a measured weight will be more. Okay, if you think the bathroom scale reads give you a normal force that's less than the weight, then your excuse me, then you'll see a measure weight that is smaller, or maybe it doesn't change. Okay, so this one I'll give you a couple minutes to discuss, and when we come back, we could work on it together. Okay. All right. So take a screenshot of the question before heading out to the breakout rooms. Hello, what do you guys think about this question here? Any thoughts, any discussions? Okay, so Elaine said, I think the measured weight will increase. That's very good. Can you say a little bit more about that? Like why you think the measured weight will increase? Does any of yours audio works? So how many forces is acting on you inside the elevator? How many forces? There are two of them, yes. And that is, we have gravity and we have the normal force from the scale. Okay, yes, so we have one more person said that, Vachu said, I also think will increase, not sure how to explain it. So let's think about all the forces. We said there's a gravity, we have the normal force, and your acceleration is upward, right? So do you think compared with gravity, is your normal force going to be bigger or smaller than gravity? So if there's a two forces acting on you, which one is bigger in order to have an upward acceleration? Is the normal force bigger or the gravity is bigger? Yes, the normal force will be bigger. Thank you for those who answered. Because normal force is upward force, right? It has to be bigger than gravity in order for you to accelerate upward. So that if your normal force is bigger than gravity, then your measured weight will increase. When you don't have any acceleration, you simply just measure your weight, because in that case, your normal force is your weight, is equal to your weight. But now normal force is a bit bigger. So the measured weight as it reads on the scale will be a little bigger than what you have had if you were just outside of the elevator or sitting abreast at the elevator. Very good. All right, I'll see you guys pretty soon in a bit when we come out of the breakout rooms. Okay. Okay, let's take 10 more seconds to wrap up our voting. Okay, sorry, I don't know why my share is gone, but let me redo the share one more time. Maybe I need to disconnect and connect back in again. Okay, sorry, it took a little while to get this back connected. All right, let's take a look at the results of our poll. All right, so we majority seem to think either we will measure an increase or it will stay the same. It's still your measured weight. As if you were 120 pounds normally, then you stand in the elevator was still going upward, accelerate upward, you still get 120 pounds, or maybe you will measure both um, more weight. So there is a hint that how much the measured weight will display will depend on how much normal force the scale provides you. So we change the problem to looking at how normal force compare with weight, right? There are two forces acting on the person right now. That's your gravity and there's the normal force because you're only in contact with the scale. So other than the long range force gravity, the only other force is provided is the scale that you're having contact with. So normal force and F of G. With acceleration being upward, you need normal force to be bigger than mg or smaller, or are they equal? What do you think? In order for your acceleration to be upward. Is the normal force going to be equal to mg, or is it going to be bigger than mg?
NG is going to be bigger.
Yeah, it's going to be, normal force has to be bigger than mg, right? So that the net force will have to be upward so that you can have an upward acceleration, right? So we know that normal force is bigger, which means that the measured weight will increase from what you had measured before, okay? Now, in other words, if your acceleration is downward, if I change this problem, say the elevator was going up, but then it starts to slow down. So you know you have an acceleration downward. In that case, your measured weight would have been smaller than if you had to measure it outside of the elevator normally in the bathroom step. Okay, so depending on the acceleration, you will have read different values from the scale. Now, the why the measure hand equals the normal force, that is a Newton's third law application. We will talk more about that when we get to Newton's third law. But right now, we're just going to borrow that piece of information. Okay, so A is the correct answer. Now let's look at a particular question with some numbers. So we say if your acceleration is upward, you're going to read a value on your bathroom scale that's more than you normally would have weight. But how much more? What does the scale read? So let's put in some numbers. I say the person is 110 pounds, which means that the mass is 50 kilograms. So now he's standing on the scale and the elevator goes upward, accelerating upward with acceleration 0.5 meters per second squared. So how does the scale read? What does the scale read? So let's try to calculate it. Okay. All right. So let's draw the free body diagram as we did previously. I'm going to draw a force of gravity pointing down. I know there is a normal force provided for the person upward. So you can see that this force is from the scale, of course, it's from here. So you can draw your arrow directly at the contact, or you can move all your forces to one center and move it, draw all the forces from this point. So either way is okay. Okay, so this is normal force. I'm going to decide upward to be my positive direction. Okay, I'm going to set up Newton's second law in that direction. So I'm going to apply it in the vertical direction, in the y direction. So let's look at the left-hand side. So how do I expand it? It's the normal force and the gravity have a vector addition. So upward is positive, so normal force is positive. Gravity is in the opposite direction, so I should write that in negative direction. So minus F of gravity is equal to ma. Okay, A is positive as well. Okay, we also know that force of gravity is mg, little mg, and that's ma. So we calculated the normal force right now acting on the person is ma plus mg. Okay. So this would be the normal force. And let's plug in some numbers. The mass is 50 kilograms. Acceleration is 0.5 meter per second squared, and little g is 9.8 meters per second squared. So because all of these is already in the SI units, which means it will give me the force in Newton units, so 515 newtons. Now, if you convert that to pounds, that is roughly 116 pounds, okay? So you can see now it is a bigger number than what you normally would have read on your scale. Okay, because the measured weight is simply equal to the amount of the normal force that you are provided with. Okay. Any questions about this particular problem so far?
I did have a question.
Yes.
Why wouldn't it be negative MA if given the equation it's the absolute value of N minus FG equals MA minus MA equals 0. Oh, never mind. Sorry, I made a mistake.
Okay. Sure. So it all has to do with the positive direction you choose. So you could have tried yourself to choose your positive to be downward and to see if you still get the same result. You should still get the same result. Okay, thank you for that question. Okay, so now let's look at the normal force, another scenario. We normal force, if you just sit in there, is going to equal to your weight. If you are accelerating up or down, it may be bigger or smaller than your weight. What happens if you are not on a flat surface, but instead on the incline, on the ramp? So how do we calculate the normal force then? So if you look at this object, the frog is sitting at rest. What is the magnitude of the normal forces acting on the frog like that? Okay, so again, in order to find the normal force, you wanted to be able to look at the balance of the forces in different directions because it is at rest, meaning the force must be balanced, right? So when we are on a flat surface, it is very intuitive to say, we're just gonna say force is balanced horizontally, force is balanced vertically. But now when you're on a ramp, we're going to change our X and Y slightly, just to make it a little bit easier. So you can see that when we say this is X and this is Y, as a little bit, it's not as easy because the normal force is neither in both in X or Y, it's kind of diagonal. So for incline problem, we often rotate our coordinates to be tilted as well. So for example, if I'm going to say this is my Y and this is my X, okay? So I'm going to tilt it, my X and Y, when we have incline problem. This is only for the sake of easy to calculate, okay? Technically, you could have chosen any X, Y you want, but we want to choose one that's easy for calculation. So in the Y direction, in the X direction. And the forces should be balanced in both directions, right? Okay, so this has to do with breaking down the weight, force of gravity, into an X component and a Y component. So we will do this a few times, but once you're familiar with it, whenever you see an incline, you should right away be able to write down what is the X component and what is the Y component. So let's look at this. How do we break it down? So this is your f of g, and the Y component is in the vertical direction that's perpendicular to your surface, right? So here you have a f of g in the Y direction. Okay. So this is your Y component. And your X component is along the ramp pointing down. This is f of g in the X direction. Okay, so if they tell you the angle of the ramp to be 30 degrees, for example, then this is also the same angle. Okay, how do we know that? Let's draw a little bit different graph here. So you can see if this is 30 degrees, this is 90 degrees, this is 60 degrees, right? And this is perpendicular, this is 90 degrees, so this little angle is 30 degrees. So this angle and this angle of the ramp is the same angle. Okay, so if they tell you it's a ramp that's been tilted 30 degrees with respect to horizontal, you know, okay, then this is also 30 degrees. With that angle, we will be able to write down f of gx and f of gy. Okay, so cosine of theta is, so cosine theta is fgy, the adjacent over the hypotenuse. So fgy is fg and cosine theta. Fg is just mg cosine theta. So this is your y component. What about your x component? It's the sine theta is this this line here, which is f of gx over fg. That is mg sine theta. Okay, so that is the component of your weight, so that now we can set up our equation in the x and y much more easily. All right, so any questions? Is it clear how to break down the gravity into components? I just want to make sure I'm either spending too much time on this or not explain it enough. So are we good on the component? Okay, all right. So if we're good on that, we can look at all the forces in the y direction, because that is giving us the normal force. All the forces in the y direction, there are two. One is normal force pointing up. One is force of gravity pushing in. So normal force is sort of perpendicular to the ramp, right? Upward, and force of gravity is down toward the surface of the ramp. When you set these up, they have to be equal in magnitude and opposite in directions. So when you do F equals ma in y direction, you simply have two forces. One is normal force, one is f of y, and that equals ma in the y direction at 0, because the frog is at rest. There's no acceleration. So your normal force is equal to the force of gravity, the component in the y direction, that's mg cosine theta, okay? So hopefully after a few of these questions, whenever you see an inclined problem, you will know that the normal force is going to be equal to mg cosine theta. Okay, so that's how we calculate normal force for ramp problem. This is a more of another sort of sketch and break it down into the x and y component. So when you have on the ramp, you have to write subscript for x and y. So you can also choose to write your gravity as weight. So you don't have to write fgx, fgy. You can just write weight x and weight y. So that might be a little bit more clear if you choose to do so. And either way is fine, okay? So this is just what we did previously. All right, so in that case, let's try to use what we just learned to look at a scenario where normal force is not simply gravity. It has to do with other forces. So we see two cases. You're either pulling or pushing on a sled with a certain amount of force that you exerted. And you exert that force at an angle. Let's think about that you are pulling or pushing a sled of a kid, helping a kid with a sled. In which case is the normal force greater? In which case the normal force acting on the sled with the kid as a whole system is bigger? The case 1 or 2, or is it the same for both of them? Okay, so think about how you might break down the forces in different components and how do you apply that to figure out the normal force. All right, I give you a little bit time to discuss it within your group. Now, I do strongly encourage you that if your audio allows you, try to talk to them within the breakout room. It's more efficient than typing. Okay, I did stop by a few rooms. I'm going to go to room, I believe room 5 next. And I'll see all of you when we come back, okay? Make sure you take a screenshot of the question before you leave, so you still have it for discussion.
How's it going, Professor?
Good, how are you?
Good, and you?
Okay, any thoughts here?
The normal force in both cases. Oh, because one's downwards. Depends on the ice surface. No. What it says depends on the magnitude of. We can take it. That means the magnitude of the force.
Yeah.
Okay.
Yeah, this is somehow covered by the picture. Depend on the magnitude of F. Sorry.
I think in case 1 it would be bigger because case 2 has an upwards component. So wouldn't that make the normal force maybe smaller because the gravity's downward force is still the same?
Yeah, so I believe, yes, we have a good intuition about this in this case. Normal force, we all agree, it's how much the support the surface gives you. So you have a heavier object, you get more support. Or if you, also depend on how hard you push on the surface, right? So if you push really hard, pushing down, then the surface will provide you with more of a normal force support. We do have a pretty good intuition on this. So if you have a heavy object but you try to lift it up, right? You are able to lift it up so it's barely touching the ground, then the normal force will be 0. So that's kind of like what you had in this case 2. You're trying to lift it up, but in case 1, you're pushing down. So you're right, with that extra component of F, either pointing up or down, it will affect how much normal force is acting on the sled, right?
Okay, so then case 2 has greater normal force because you're pushing down. Okay, that's cool.
Case 1, I said case 1. You're right. It's the case 1. Case 1 is where you push down.
Oh. Sorry.
Yeah, case 2.
I misread the case numbers. Yeah.
Yeah.
Okay.
Sorry. We can build upon our intuition, but to get the specific value, we will just set up Newton's second law.
Okay.
What about the rest of you? What do you think? Any questions? Dylan and Justin and Mark and Maxie? Any questions? All right, I'll see you guys in a bit when we come out of the breakout rooms. Okay, yes, Dylan, thank you for responding. You agree with normal case, normal force greater in case 1. Okay, I'll see you guys in a bit. Sorry. Okay, let's run for another 10 seconds. All right, any last minute vote? I'm gonna go ahead and close it. So I believe for this case, we have a very good intuition. Our intuition can actually help us answer this question. So if you have an object on the floor, how might you be able to increase or decrease the normal force? What would you do to increase or decrease the normal force? So if you have a book sitting on the table and I ask, can you increase the normal force the book is acting on the book? What would you do?
I would push on it.
Push on it. Very good. So the harder you push, the more of a normal force, the more of the force that the table will support the book. Excellent. What would you do if I say, now decrease the normal force of the book?
You would kind of pull it back in the opposite direction.
Yes, and we provided upward, try to lift it up, right? You can, in fact, lift it up so that it's barely touching the floor or the table, then you have 0 normal force. So here, this is the exact same case. You have case 1, where you're kind of pushing down in the diagonal way. Case 2, you're trying to lift it up, right? So of course, the case 1 will give you a bigger normal force, and case 2, you have a smaller one. Okay, so the answer would be A. You could set up Newton's second law to calculate the exact number, but qualitatively, we're able to use our intuition to answer it. Okay, now let's look at this question. here we have a block sits at rest and stays at rest on the slide on the incline. Which one of this sketch is a correct free body diagram of the block? Okay. So this one I would just have you vote. It's a recap of all the incline problems we have been doing so far. So just go ahead and put in your thoughts. Which one of these is a correct sketch? All right, any last minute votes? A few more seconds. Okay, perfect. Okay, I'm gonna go ahead and end the poll, okay? And to look at the distribution of the results, looks like we all agree on two of the forces, normal force and gravity. We all agree on that. Now I would say the B and C, okay, so we did talk about how to break down gravity into two components. So I do understand why you might want to choose B or C, is maybe you're trying to draw that component. So I just wanted to clarify is when we have gravity already, we're not going to draw the components as a free body diagram because that is not a new force. That is just a component of the force that you're being applied. Okay, so it's not a new force. So we're not going to draw the components at first for the free body diagram. But sometimes when you try to use your diagram to set up your force equations, you do have to break it down. In that case, we will sort of cross out our gravity, simply place the X and Y component, but we do cross out our gravity, showing that, hey, we have already considered this force. It's replaced by these two other components, but we're not double counting, okay? So that's why we don't choose B or C. Now, the majority, you agree on A or D. There is the upward force, perpendicular surface, that's normal force, the downward is gravity. The only difference is there's one has friction, the other one does not have friction. So the question didn't really explicitly tell us, but do you think we have friction here?
I think we do, because if you were going right now, the component force, it has a horizontal component, right? And that would lead us to believe that the block isn't at rest. So we do need some sort of friction.
Yeah, with A, you can see the addition of these two arrows give you an overall net force going down. But this block is at rest. So to have a balanced total force, you do need a friction. And the friction must be upward, like what D is showing, right? So you need a force pointing upward. So D is correct. Okay. So now let's talk about friction. So we have looked at different scenarios of normal force when you're pushing on or pulling or lifting on the surface, normal force when you tilt it, normal force when you accelerate upward or down or decelerate. We have looked at all the various scenarios for normal force, but how do we deal with friction? Okay, so there is a static friction and the kinetic friction, and they have to be dealt with differently. Static friction is not a fixed value. Static friction is always equal to the force acting in the opposite direction. And why is that? Because it's static, meaning that whatever force you're trying to apply is not enough to give it an acceleration. It's still sitting there, right? So let's say you have a very heavy table and you try to push it, but you pushed it with, let's say, 500 newtons of force. It didn't move. Why? Because the floor must provide it 500 newtons of static friction in the opposite direction of where you're pushing to keep it from moving, to keep it from having an acceleration. But if you decrease your force to 400 newtons, then the floor will simply provide 400 newtons of a static friction. So static friction is constantly changing. It depends on what force is in the opposite direction. Okay. However, the kinetic friction is a fixed number. It is proportional to a normal force acting on the object. So this is also quite intuitive. If I say, if you have an object sliding through the floor, if you want to increase the kinetic friction, make it more difficult to slide across, what would you do? You might say, okay, I'll have stack a book on it, make it heavier, right? That will make it harder and more of a friction, right, to slide across. Or you might say, well, I'm going to put some sandpaper on the floor. That also works because you're changing the surface. So both of those will affect your kinetic friction. How rough your surface is, the nature of your surface is described by mu of K. That is the kinetic coefficient, simply describing how rough or how smooth your surface is, and also depends on the normal force. The bigger the normal force, the bigger of a kinetic friction. So kinetic friction is mu times n, okay? So if we have that equation, we're not able to solve the very first problem we begin our class today is finding out what is the magnitude of the force you applied. We know that the force from the hand is equal to kinetic friction. So the force from your hand is equal to kinetic friction, and kinetic friction is mu times the normal force, okay? The normal force have already been calculated, equal to the weight of the book is 2.5 pounds. You multiply that by the coefficient, which is given to you. Describe how rough your surface between the book and table is 0.2. So 0.2 times 2.5 pounds give you 2.5 pounds give you half a pound. So that is the force you provide from your hand. We're not able to answer this question because we know how to calculate kinetic friction, right? So it's mu times n, the normal force. All right. So for kinetic friction, we know that for static friction, it's always changing depending on what force is in the opposite direction. So if you if say originally the frog is sitting at rest on the horizontal table, but then as you lift it up, you can see that the surface will have to provide more and more of a static friction to prevent it from sliding down, because the force now is trying to act in the opposite direction is along the ramp is getting bigger and bigger, right? So we have done this before. The force is sliding down the ramp is mg sine theta, as we did here, okay? So fg of x, the component of gravity along the ramp is mg sine theta, okay? So prevent slipping in that direction, you need to provide a static friction that is in the exact same magnitude but opposite direction. So you have to provide a static friction that is equal to mg sine theta, right? As you can see that when you lift the ramp up more and more, the angle theta becomes bigger and bigger. So sine theta becomes bigger and bigger. This component that's trying to get it to go down is bigger and bigger. So you need to provide a static friction that's bigger and bigger. But there's only so much static friction you can provide. After you exceeded the maximum amount of static friction, then it will start to slide. Once it starts moving, you're going to have kinetic friction. So if you calculate the kinetic friction is a totally different, you can see it's a totally different equation because that's mu times n. N is mg cosine theta for the ramp. So it's mu times mg cosine theta. Okay, so for a ramp problem or any other questions, if they ask anything about the friction, first of all, look at whether it's a static friction or is it a kinetic friction. Okay, depending on which one it is, you will choose to use different equations to solve it. Okay, all right. So so that's all we're going to talk about today. For Monday, we'll continue to do more Newton's second law applications. And if we have time, we'll go to Newton's third law, but if we don't, we will continue just to solve different kinds of combination of Newton's second law problems. All right, any questions so far?
Are we gonna have a review before like our midterm?
There is a practice exam online, so you can look at that as a review. Right now, I uploaded exam. I want you to work on it by yourself. But later on, I will upload a solution so you can compare your work to my solution.
Oh, and when is the midterm exactly?
When is the midterm? It's in the course calendar. It's not next week. So let me see. It's going to be Wednesday, October 6th.
Okay, thank you so much, Professor.
No problem.
Professor, sorry, I got cut off. You said that there was a practice test on Achieve, I believe.
It's on Canvas.
It's already
it's already there. Yeah.
Oh, okay.
It's already. Okay. It's under week 5 folder.
Okay, thank you.
Okay. Have a good weekend. I'll see you guys on Monday.
Professor, sorry, I was waiting for everyone else to ask their questions. Is it possible for you to upload? I think sometimes you wait until a little bit after class. Could you upload today's PDF of the notes as soon as possible? Please, sorry, there was some notes I couldn't get that I was trying to fill out my notebook with.
Yes, absolutely.
Thank you. Have a good day.
Have a good day.
Oh, sorry. One last question, Professor. I was a little confused because last time we only had a free body diagram pointing down and up. How come for this one the answer was D? Because I remember last time the answer was just down and up. Is it because the static friction? Because last time we had the same that one right there.
This question?
Yeah, we had the same thing, but I remember A was the right answer. So.
Oh, that must be a question where it says a frictionless surface.
Oh, okay. So if there is a frictional surface, there's okay, frictionless. I see. Okay.
Yeah. So this one you can see it's sliding down.
Yeah.
It cannot stay there.
Okay. Thank you so much, Professor. Oh, last thing. Sorry. I keep thinking about it because I always try to review a little bit before I go. You said if acceleration or if velocity is constant, then there's a zero force, right? If velocity is constant.
Yeah, the net force must be all balanced to give you a zero total force.
Okay.
Yeah.
Thank you.
Professor.
Yes.
I also wanted to know if you will be having office hours today because today's Friday, huh? I wanted to know if you could help me out with problem 5 of the homework.
Okay. And would it work if I post solutions to the homework 5, question 5?
Yeah, sure, that's fine.
Okay. And you can look at it, and if you have questions, you can always email me to set up something sometime to meet. Okay.
Okay, that sounds good. Thank you.
Okay, and responding to the question in the chat, I will post solutions to the practice exam, but I want you guys to work on it first. So next week I'll post solutions. All right, bye everyone.